Well, hello and happy Sunday. It's snowing here in Pittsburgh, and I hope you have a more clement weather. Today, I'd like to do a very brief presentation on the standard model of quantum mechanics. The standard model is a system of thought and hypothesis that forms the very basis for the field of quantum mechanics. Now, I understand that the field of quantum mechanics is a very intricate subject, and my very crude survey or presentation is probably not going to scratch the surface even. Nonetheless, in this presentation, I would like to present some of the big ideas, general concepts, and also some of the particles that are most commonly studied in the field of quantum mechanics. And I hope these can pique your interest a little bit. And also I recognize that the quantum mechanics may appear to be a very abstract thing to us. So I think it's always good for us to remember that what we're truly doing here is we're trying to understand nature. So we're doing natural philosophy. Now, if I'm not greatly mistaken, I think you can see from the name quantum mechanics that it has to do with quantized units, or particles. This idea of particle, I think, harkens all the way back to the idea of an atom, which is an indivisible particle by its name. Now, we now know that atoms, in the way that we refer to them in physics, are actually not indivisible. They're subatomic particles, electrons, neutrons, and protons. Nonetheless, this idea of there are certain particles that are so fundamental that they are no longer divisible is a central concept and theme in quantum mechanics. Now, here I have for you some particles. Now, this one is the construction of a proton. Now, these subparticles you see here are actually quarks, which we'll talk about later, which are particles also. But they collectively make a proton. And a proton is also a member of a class of particles called the hadrons. Here is a pretty typical rendering of a photon. Now, a photon is a unit of light or electromagnetic radiation. Here I have an electron for you. And I chose this image because it really reminds me of the duality of an electron being both a wave and a particle. And electrons having pretty less mass, light mass, is part of a group of particles called the leptons, which have relatively small mass. Here's one of this interesting particle called a graviton. And what gravitons do is supposedly they're being emitted and absorbed by different masses. And this micro process of absorption and emission, the overall trend of attraction between bodies of masses, between stars, for example, are actually observed. And we have more to say about gravitons, which are a type of mediated particles later. And now, while we are on the topic of terminology, of defining what particles are, I really want to emphasize the point that particles do not have to have mass. For example, a photon has no mass, right? A light has no mass, yet we consider a photon as a particle. And also, I think one other important idea in quantum mechanics, in the standard model, is that mass is actually a form of energy. I have here for you the famed equation by Einstein. What this equation reveals is that mass and energy are actually interconvertible quantities. In fact, in nuclear power plants, what we do is we try to release the energy that is contained in the form of mass and harness them in terms of heat. And also, you can also go the other way. When you have energy, you can also turn them into mass in certain ways, upon certain occasions. So this idea that mass and energy are interconvertible is another central idea of quantum mechanics. Now we get to talk about the standard model. Now the standard model dictates that all interactions, all reactions, everything, literally everything that happens in our nature is a result of 4 types of fundamental interactions. And they are, first, the strong interaction, second, the electromagnetic interaction, third, the weak interaction, and fourth, the gravitational interaction. Now, we may be more familiar with the second and the fourth, right? Like electrostatic forces and magnetic forces. They are part of the electromagnetic interaction. And, gravitational forces, gravity between stars are a type of interaction that's classified as gravitational interaction. Now, one example of a strong interaction may be the strong nuclear force that's being observed by a neutron and by a proton, which helps stabilize the nucleus. An example of a weak interaction may be the process of a beta decay, in which you have a neutron decays into a proton and also an electron. So this process of decay is actually under the influence of a weak interaction. Now the Standard Model also answers for the question that what are the fundamental particles? What are the most fundamental particles? And it says there's three. So the first class are what we call leptons. Now as we said earlier, electrons is one type of lepton. It's one of the leptons. And the second class are quarks. And quarks collectively make up a class of particles called hadrons. Now hadrons in turn have two types. One type of hadrons we call nucleons, which is just a general name for neutrons and protons. The other type of hadron is actually something called mesons. Now the third class of fundamental particles dictated by the Standard Model is the interactive or mediative particle. Now if you recall back to the example of a graviton is actually a mediative particle. And what the fundamental particle of mediative particles mean in terms of the Standard Model is that all interactions between particles are actually affected by particles, by those particles called mediative particles. For example, let's say we have two opposite charges, right? A positive charge and a negative charge. Well, the reason that they actually attract each other, that we observe that they tend to attract each other, is that one charge actually emits a photon, which is received and absorbed by the second charge. Now that second charge also, in turn, similarly emits photons that are absorbed by the first charge. So by this micro communication of photons, from this micro communications of photons, we observe the macro phenomena of attraction. And also, there are conservation principles in the Standard Model. We're all familiar with the conservation principle of, like, for example, the conservation of energy and the conservation of momentum, which are conserved in all reactions and processes. But there's also the conservation of certain quantum numbers, and we'll see some of them later. Now, as we said, leptons, of which electron is one of them, are particles that are relatively light. Well, they are actually particles that are not involved in strong interactions. So, for example, electron is not involved in a strong interaction between neutron and proton, and hence is classified as a lepton. In fact, there are 6 leptons. The first is an electron, the second, an electron neutrino, the third, a muon, the fourth, a muon neutrino, the fifth, tau, the sixth, a tau neutrino. Now, you may see some patterns right here, right? Essentially one particle accompanied by the particle neutrino. Now, in fact, there's 3 lepton numbers. The first lepton number is the electron lepton number. The second is the muon lepton number. And the third, as you probably guessed, is the tau lepton number. And they are all conserved in all kinds of interactions and processes. So this is one of the examples of a conservation of a quantum number. Now, another type of fundamental particles are quarks. I'd like to first talk about what inspired people to think that there are quarks. Now, the quark model, if you will, is actually inspired or partially inspired by the existence of neutrons. And what I mean by that is, if you think about a neutron, right? A neutron has no net charge. It has no charge, in a sense. But it has a net magnetic moment. And we know that a charge, for a thing to have a net magnetic moment, there must be a movement of charges. Well, we just said that neutron has no charge, or no overall charge. So what the quark model proposes, what the quark theory proposes, that a neutron in this middle right here, this middle diagram, is actually composed of one up quark, which has a net charge, a net positive charge of 2/3, and 2 down quarks, which each has a negative charge of -1/3. So when you add them all up together, they actually contribute to a net 0 charge. But nonetheless, the movement of these subparticles, these subcharged particles, contribute to the net magnetic moment that we observe of a neutron. So this explains the neutron. And also, charge is not the only thing that is being divided, as you probably guessed, in a neutron or in a nucleon. But also a quantum number called the baryon number. Now we assign a baryon number of 1 to each nucleon, to each proton and neutron, and then correspondingly, each quark actually has a 1/3 baryon number. And so when you add up all the quarks together, you get 1. So this also means that every nucleon, every proton and neutron must be composed of 3 quarks. And here I have a proton for you. Now, you may say, well, okay, there are there are quarks inside a neutron or a proton. There are quarks inside these particles, inside hadrons. But how do they interact, right? So as we said before, that all fundamental particles and all particles in general interact through mediative particles. And so there exist these mediative particles called gluons, which actually interact, help bind the quarks together, help, make them interact. Now this image right here, if you observe, is actually more similar to the second than the first. In fact, you see that it's actually identical in a sense. The only difference is that you have these little dashes above every quark. Now these dashes above actually indicates that these are not quarks, but anti-quarks. And this diagram right here in general, in whole, collectively, is a diagram of a particle we call an anti-neutron. Now an anti-particle is a particle that has the same mass with the original particle, but have different electromagnetic properties. So what we see between the neutron and an anti-neutron here is that the relationship being a particle and an antiparticle on the level of a neutron is actually reflected in the quark and anti-quark corresponding relationship in a subneutron level. Now, one interesting example of antiparticles is actually the discovery of positrons, which are the antiparticles of electrons. And this has to do with the English scientist Paul Dirac's concept of vacancy. Now, you see in the diagram right here that an electron can have positive and negative energy states, but it cannot have energy states in between, right? You can either have energy states greater than its mass times the square root of speed of light, or it has to have energy lower than negative of that magnitude. So, when an electron is actually at a negative energy state, it's actually unobservable in a sense. But when it absorbs a photon energy greater than the gap of greater than 2 mc squared, it's going to swap from a negative energy state. It's going to be elevated to a positive energy state and becomes observable. But in this process too, it leaves behind a shadow in its vacancy, a particle called the positron. And this positron is actually an antiparticle to the electron, such that when the electron emits a photon, or emits photons, with energy greater than 2 mc squared, and returns back to the state of negative energy, it's going to combine, it's going to fuse it somehow with the positron, and they're going to eliminate each other while releasing additional energy. Now, after giving an overview of the standard model and also some key ideas in the quantum mechanics, I'd like to conclude by comparing some specific interactions. And the three I picked is the first is between is internuclear force, so the force between a proton and a neutron. The second is electrostatic force, which we are more familiar with. And the third is the gravitational force. You may observe from the second and the third that they are actually very similar in form. And in fact, if you treat r, the radius vector, as the only variable, you mark that they only differ in terms of the constant. And you actually observe, when you consider the internuclear force, F of n, that when the constants are not, which is a constant, and F is also a constant, right? When R naught and R are somehow close to each other, this term right here becomes some multiple of R, and this term in the denominator becomes some multiple of R cubed. So if you simplify the term in that sense, it's going to resemble something like the inverse relationship of R squared, which is also observed in the electrostatic force and gravitational force. So this similarity of interaction in terms of the equation actually prompted people to suggest that all the 4 types of basic interactions, all the 4 types of fundamental interactions, are actually variations of one uniform type of interaction. And there are scientists devoting their time and energy to see if this interaction actually holds. And I think, personally, that if one day it is said that they are indeed, all types of interactions are variation of one type of interaction, we can truly say it will be the most cogent statement to our belief that nature is one. Thanks for listening.